Hello and welcome to today's SQL Office Hours session. Today we're going to be looking at fuzzy matching with SQL. So before we do that, let's just imagine you at work and your bosses ask you to complete a task to run a script to give all Stevens pay rises, right? Everyone who's called Stephen. So at this point, you run a script and, we'll update the employees where the first name equals Stephen and they get 5% pay rise. So at this point, everyone called Stephen is like super happy, right? Like party time, I got a pay raise, great day. Of course, all the rest of us probably aren't too happy. We're like, oh, well, I'm not called Stephen. Why don't I get a pay rise, right? But there's some people who are called Stephen who are probably unhappy as well, and probably even more unhappy than the rest of us. And they're the ones who spell Stephen with a PH, right? There's two kind of common variants of spelling the name Stephen, with a V or with a PH in the middle. And we wrote that script, so we only gave people called Stephen with a V a pay rise there. So, all of us not called Stephen would probably be a bit upset that we're getting nothing. But I think the people who are called Stephen but had a slight variation on the spelling of their name were really upset at this point, right? So that's kind of what we're going to look at here. How can we find similar sounding names or names with slight variations in the spelling so we don't kind of run into these kinds of problems? So that's what we're going to look at today. So hi everyone, I'm Kris Saxon. I'm part of Gerald Wenzel's app dev team here in Oracle. It's my job to help you get the best out of Oracle database and hopefully have fun whilst doing so. As I say, we're going to be looking at various approaches you can use to do fuzzy matching in Oracle SQL. I'm going to be running lots of demos in this, and all of the demos are going to be running on the Oracle Autonomous Database 23 AI on the cloud free tier. So this is completely free. You can sign up. You can get up to 2 autonomous databases, which have up to 2 CPUs or whatever we call them now, eCPUs, OCPUs, I forget. And I think it's 20 gigs of storage so that you can use those for whatever you want, really. So check those out if you want to run the demos that I've run through. I'll share the scripts if you want to try it out for yourself later. So that's what we're going to do here. So the question is, how can we find people with similar sounding names? So we want to find 2 lots of people called Stephen. We want to find them with S-T-E-V-E-N and S-T-E-P-H-E-N, right? So one approach we could take is to use kind of wildcards. So we can say like, and then we got some character, there's V or PH, and ignore the ones which are ambiguous in terms of pronunciation, right? They sound the same, but actually are different letters. So sounds straightforward enough, but there's two kind of big drawbacks to this approach. First up, how do we know which letters sound the same, right? I mean, there's quite a lot of them, right? And some, depending on what they're next to and where they are in the word and things like that, can sound differently, or have lots of a variety of different pronunciations. And some pronunciation depends on your dialect as well. What's your primary language? The other problem with this kind of wildcard approach is we might end up with a lot of false positives. They're relatively rare, but there are some names that begin STE and NDN and sound nothing like Stephen or at all, right? Steuben and Stellan and things like that. We probably don't want to accidentally include those as well. So we'll look at using wildcards. So another approach we could do is encode the strings. And there's a very common algorithm called SOUNDEX. It's very old. I think it was about 100 years ago it was first developed. And it was developed to help kind of match names that sound similar but actually have different spellings. So we can map those and hopefully we'll find things that sound the same. But the problem with this is, well, what is the rules for the encoding? How is SOUNDEX actually work? As we'll see, it's actually fairly simple rules and it misses a lot of potential matches. Finally, another way we could approach finding similar sounding things or similar names is just to kind of count the differences in the strings. So we've got Stephen with a V and Stephen with a PH. We could say minus the V and plus the PH. Depending on how you count that, there's either 1 letter change or 2 letter changes, and count how many differences there are and match things based on having relatively few differences. But again, a bit like with the wildcards, we can have false positives, match things which aren't really the same at all. Essentially, we could have this as well. Instead of matching PH, it doesn't distinguish between PH and double L or something like that. So that's three things we're going to look at to start off. We're going to look at wildcards, we're going to look at encoding with SOUNDEX, and we're going to look at using changes. And we're going to use the UTL match package, which has some functions in there to actually count the differences and compare strings. So at this point, well, let's just jump into it. Let's look at the demo, and I'll bring things up here. So hopefully we've got things, and we can see we've got our classic employees, and there's a few people called Stephen. So there's 3 rows, 2 with a V, 1 with a PH. And we want to identify all of these. So like I say, one thing we could do is use like wildcard matching. So there's actually 2 ways we can find the ambiguous or the missing characters or the ones we're not sure what they are. You can use the underscore, which matches exactly 1 character. So we can see STE_EN. That will only match Stephen with a V because there's only 1 letter that it's actually matching. It can be matching any letter, but only 1. If we put 2 underscores in there, we're matching exactly 2 characters. So we'll find our Stephen there as well with a PH. Or we can use %, and that matches any number of characters. Could be none, could be however big the string is in total. And we do that, and we can see we pull back all the Stephens. Like I say, there is a chance we'll pull back some other matches as well. So let's look at a different example. Let's say we're going to find people with the surname, family name Lee. So in the employees table, there's 2 different variations on this. There's LI and LEE. Both of these I would pronounce Lee. They sound the same to me. So we want to match both of them, right? And again, we can't use the underscore because we don't know if there's 1 or 2. So we're going to use %. Unfortunately, what's going to happen if we use L% here? Well, we're going to return everyone whose surname starts with an L. And so these are clearly people who don't match at all, right? So we're getting Landry and Ladvik and things like this. So that pulls back a lot of unwanted matches. So like can work pretty well if you're quite sure about most of what you're searching for, but it quickly falls apart when we get into these kind of ambiguous sounding things and stuff like that. So let's look at SOUNDEX. And like I say, this is, I think it's over 100 years old now, but it was kind of popularized by Donald Knuth, who wrote a book in the 50s, I think, explaining the algorithm. And it's quite a simple algorithm. Take the letters, map them to some characters. So if we compare this on Stephen, and we can see, it's returned all the Stephens that we want here. And they all have the SOUNDEX code, S315, right? So they all map to the same thing. So this is sounding pretty good. If we do the same for our family names, our last names with Lee, again, we get both back because they both have the same SOUNDEX. L000, it's 0 because it doesn't actually match anything, right? It just matches the L in effect and ignores the vowels in this, the E's and the I's and so on. So we can use SOUNDEX, and so far this is looking pretty promising. But let's dig a bit further. Let's look at some more variations. So what about variations on, like my name, on Kris? Well, let's say people called Christopher, for example. So you can see there's 1 person in the table with the first name, Christopher. Now, the interesting thing about Kris, Christopher, and so on, there is a lot of ways you can spell this name, which kind of sound the same. One of which you can do is swap the CH for a K, okay? And certainly I would pronounce this exactly the same, Christopher versus CH. Do that, and we have not matched anything at all, right? So they have got different encodings. So why is this? Well, one of the key things about SOUNDEX is it always preserves whatever this first character is. It doesn't matter whether they sound the same or not. It always keeps it. So we can see Kris, CH, and Kris with a K are mapped to the same, okay? So they're considered different, and that's because SOUNDEX Kris begins with a C, and SOUNDEX Kris with a K begins with a K. So automatically they're going to be different. So that hasn't really worked here. So I see someone's got a question. SOUNDEX last name, SOUNDEX Li, Lee, also works. Yeah, that also works. So we just swap that in here and say that's what we're saying. is they are identical. Essentially, it ignores all the vowels in this, okay? You can look up the algorithm if you want to. There's a fairly simple set of rules, only like 10 or 15 of them. So yeah, so those do match, okay? So we got Kris and Kris. So this is already a problem here. But there's also another problem when it comes to names that kind of are like Kris, right? Let's look at Christina and Christopher, okay? Now, I would certainly consider these different names. Christina is generally a feminine name, and Christopher is generally a male name, so already they're quite different. What does SOUNDEX think? Well, SOUNDEX thinks they are in fact the same. Interesting. Why? Well, because there's always 4 characters in SOUNDEX. It's exactly 4 characters long. And we've kind of used everything up when we get to Christ, right? So it ignores the ina and the ofer on these. So that is completely ignored. So we get a false positive match here. Also, a slight consideration, Kris is an acceptable abbreviation for both of these names. But it's too short, right? It's C620 because there is, if we put the T on the end there, you'll see it actually matches to the same. If I can do that, you can see that goes to the same now. But you know, we might be searching for a Kris. Where I am. And we might be searching for a Kris, which is a Christina or a Christopher. We might want to match both of those, and neither of them will, because it doesn't have enough characters or sounded characters to have a full match. So this works in very basic cases, but very quickly kind of falls apart. All right, so what about fuzzy matching, or ways of kind of comparing the changes in the string? Like I say, this is in the UTL match package, which has been around a very long time. I don't know when it was added. It's, you know, if you're using Oracle database, I'm pretty certain you've got UTL match available. So it's a couple of functions. There's the edit distance function, which is essentially the Levenshtein algorithm. And really, that's just counting the number of characters that change between the strings. So if we run this, we can see Stephen to Stephen, well, that's exactly the same, 0 changes. Stephen to PH, we got 2 changes. So we've changed the V to a P and added an H, right? So how many characters did we change here? The similarity is just that kind of scaled between 0 and 100, okay? So 100 is perfect match when there's 0 changes, and 0 similarity is when every character has to change. There's no characters in common whatsoever. So that's Levenshtein. There is another, so that pulls us Stephen, and we can see if we look at Christopher with a K versus a CH, that gives us quite a good match, right? 82% similarity because we only need to change 2 characters. Swap the C for a K and drop the H, or whichever way around we do it. However, let's look at Lee. Now, Lee, we look at Lee, we get 2 changes. Lee double E, 0 changes, 100% match. Lee LI, 2 changes, and a 33% match, a 1 in 3 match. Because if you think about it, only 1 character in 3 is actually the same. By default, it matches to the length of the longest string, so 3 characters. We're saying they only have an L in common. So this seems like quite a low match, right? And certainly if we compare it to the other ones and we just sort by this similarity, see how similar they are, we can see someone else pops in between Lee with a double E and Lee with an I, and that's key G, right? Because we just need to swap the L for a G. Like Levenstein's literally just counting how many characters do we change in the string to make one equal to the other. So G is closer to VEE than LI, which, yeah, okay. Is that right? I don't know, right? What are we searching for here? Okay, so that's one algorithm. Another algorithm is Jaro-Winkler. So this is, Jaro actually came up with the algorithm originally, and then Winkler kind of refined it a bit. So this includes the concept of different distance, how close the actual characters that are in common are next to each other. So we do a Jaro-Winkler. So by default, this is 0 to 1, which is essentially a percentage. So the similarity actually just multiplies that by 100, really. Again, exact match 100, Stephen with a PH, getting a slightly higher match, about 89% match for there. We look at Christopher again, we can see 90% match. That's better than Levenshtein here. Similarity 90%. However, when we look at Lee, this is things get more interesting again. Notice our Lee LI drops further down the list. Okay, they have a higher matching score of mid 60s, but a lot of other people more closely match LEE according to the Jaro-Winkler algorithm. So we've got, and that's because they've got more characters in common. Like G and Lee both have double E. There's Ellie and McLeod, double E and Feeney, double E and Green, lots of E's in Everett, right? So these are all considered better matches than LI. Is that what we want here? I don't know, right? So you can see this is kind of getting a bit murky and messy. Okay, so at this point you might go, well, we've got these two algorithms, Levenshtein and Jaro-Winkler. What's the real difference between them, and why would you use one or the other? So here's some examples. Just they're not names, just letters to hopefully help this make a bit clearer. So we've got A and AA and AA. They're identical. So unsurprisingly, they have an exact match. They're both considered a perfect match. So just kind of help make the comparison easier, I've used the similarity because that's like a scaled percentage for both of those. If we look at AAC versus 1AA, with Levenshtein, we need to change the A to a 1 and the C to an A. So we need to change kind of two characters, a 1/3 match. But Jaro-Winkler is kind of looking, is going, well, there's an AA here and there's an AA there. So actually they are more similar. So it gives it a much higher match. And this becomes a bit more clear if we look at AAB versus 1/2 AA. Levenshtein says they don't match at all because every single character changes if we look at position by position. Whereas Jaro-Winkler, like I say, includes the concept of distance. Well, there's this AA, which is also matches an AA, which is within half of the length of the string, within two characters. If, however, we stick a fifth character in here, AA at the start to AA at the end, now they both have 0 match. So Jaro-Winkler is heavily biased to matching the characters at the start, which generally makes sense, right? Usually the beginning of how things sound, we're kind of at least vaguely familiar with or more certain about. Not always, as we saw with Christopher K versus CH, but generally. Things also kind of get interesting when there are excess characters before and at the end. So Jaro-Winkler, AA to AA with stuff at the end, Jaro-Winkler considers these strings very highly matched, okay, 82% here. Whereas Levenshtein says, well, only 1/3 of them actually match, okay? Whereas if we stick those AAs at the end, Jaro-Winkler says they don't match at all, right? They're completely different. Whereas Jaro-Winkler, Levenshtein, I should say, says we can just delete these leading characters and get a match there. So if you want to kind of be biased to matches at the start, which is generally when we're sounding things out, is reasonable, then you want Jaro-Winkler. Levenshtein is literally position by position matching. Again, these are kind of standard algorithms. You can look them up. They're not, we've just implemented them in Oracle database. You want to check those out. Okay, so Levenshtein changes the position, Jaro-Winkler matches at the start. So if we want to find people with names like Stephen, probably one of the best ways to do it is pass them into one of the algorithms and then sort by the match descending to find what's similar. And then we'll have some cutoff. So we've got the first 5 rows with ties. Excuse me. That's including the first 5 rows and everyone who's got the same value for JW, the Jaro-Winkler, as the 5th. So Nina, you can see these have all got 70. And so these all kind of match kind of reasonably. The Stevens are all top. Good. That's good. And we get Sean and Nina and some Kevins here. Notice Levenshtein rates Nina quite low, but Jaro-Winkler rates it quite high. So you need to kind of think about what it is you're actually matching here. So any questions or comments on that before we move on? So that's kind of the basics of Jaro-Winkler and Levenshtein, which we can do with the UTL match package in Oracle database. All right, let's just kind of recap. So like I say, we can find similar things with wildcards. So like exactly one character or zero or more characters, you really need to know exactly what you're searching for to be able to use like. We can encode things using SOUNDEX, but this has got a lot of limitations to it, right? It has to match the first character, and there's only 4 characters in the encoding. Or we can count how many changes there are using a couple of different algorithms, Levenshtein or Jaro-Winkler. Okay, so those are our approaches. And frankly, at this point, I'm not sure any of them are that great. So someone says, is it language dependent? So no, these ones are not language dependent. Like say with Jaro-Winkler and Levenshtein, they're literally just checking the number of characters difference, right? You notice when I had numbers, they even work on numbers, right? So if I make this a 1, if I change that to a 1 there, we'll see that, where have we gone here? There we go. Levenshtein increases. It hasn't actually made any difference to Jaro-Winkler. It's literally just what characters have changed. It doesn't take into account how they sound or what the language is or anything like that. It's just character by character matching. Okay, so that's another important thing to kind of think about here. You know, as I said, some characters are different but sound the same depending on where they are in the word and language used and things like that. So no, they are not language dependent. Okay, so let's see. Well, let's say then at this point, I'm not convinced. I'm not sure any of these are very much good. So, what can we do in 23 AI? So Oracle Database 23 AI. So there's actually a number of options we can do to help here. First up, there is improved options for encoding. So we saw Christina and Christopher with SOUNDEX encoded to the same thing. We can use the double metaphone algorithm to allow us to differentiate them so they get different values here. Another thing we could do is kind of count or look at how many characters they have in common in terms of pairs of characters or longest common substring, things like that. So what the common bigrams and trigrams are, things like that. Finally, we might want to look at case insensitivity. You know, Stephen in lowercase or mixed case or capital case versus Stephen with PH fully in uppercase. We probably want these to match as well, at least reasonably well. And we can do that. We can look at doing that too with collations. Now, collations actually have been around since 12.2, so quite a long time now. But there's some details to be aware of in 23. So let's look at those. What we can do in 23 AI, we can encode the strings with double metaphone, find common strings, n-grams, and longest common, and look at handling mixed case strings or different case strings. All right, so before we get into that, let's just recap quickly on SOUNDEX. The problem with SOUNDEX, right? K is not pulling back Christopher, and Christina is matching Christopher. Both of these are kind of undesirable, right? So let's look at phonic encode, which uses double metaphone. Now, this has very complicated rules. I'm not even sure what they all are. You can't, but this takes into account pronunciation of the words. And this, with Christopher, does actually match CH Christopher. K Christopher matches CH Christopher. They map to the same metaphone. But by default, it is still just 4 characters. So Christina and Christopher both match to Christ, right? Which is not really what we want here. The good news is we now have an optional parameter of how many characters we want to encode. So it can be anything from 1 up to 12. So 12 is the limit. So we can do this and do a 12-character encoding of Christina and find it no longer matches Christopher, which is what we would like here. So if we kind of look at that, we can see, we look at phonic encoder Kris and Christopher. By default, they're false because default 4 characters, and there's only kind of 4 significant characters according to metaphone. So we look at 3 characters. That's why by default they are different. And if we shorten to 3 characters, then actually we can find Christina and Christopher could be a potential match for Kris because they're both common shortenings of those names, or Kris is a common shortening of both of those names. So we can tweak whatever length of encoding we want to actually match here. So that's Christina and Christopher, and we looked at the Ks. Now, let's move on a bit, and let's think about this. Right, we've got 2 names here, and I'm not going to say them. So we've got Jasmin and Yasmin. are these pronounced the same, right? What do you think? Do you think these are pronounced the same? Well, if you ask me, I would say by default, as a British speaker, that they are pronounced differently. I would say this is Jasmine with a J, and this is Yasmin with a Y. And Metaphone considers them to be different as well. It says they are different because Jasmine encodes with a J and Yasmin encodes with an A. Okay. However, there are probably some of you watching this and thinking yourself, this with a J, that's not pronounced Jasmine, that's Yasmin as well, or Yasmin, right? They both are pronounced the same. And this is, someone was asking about languages. Different languages pronounce these differently, or different dialects. Phonic encode has an alternate, there's a double metaphone alt, which accounts for these different pronunciations. And if we look at the alternate double metaphone, it does say that these are the same. They are in fact both Yasmin or Yasmin, right? And they encode to the same string. So we also have another way to find things which sound similar depending on what your dialect is. All right, so again, there's a whole stack of these rules. There's too many. I'm not going to bore you with all the details. You can look them up if you need to. And you can see we just kind of compare the alternate spellings for the first and last names for the people in the employees table. There are quite a lot of situations where one or both of these are considered different based on the kind of language pronunciation. The big one is like names that start with J, where it's a J or a A. All vowels and Y's map to A at the start with metaphone. Okay, so we've got more options so we can find things more easily which sound the same. So that's phonic encode. So that's looking like a much better approach, certainly much better than SOUNDEX for finding things. What about fuzzy matching? Let's look at fuzzy matching again. So before 23AI, we had to use that UTL match package. In 23AI, we now actually have a native SQL operator called fuzzy match, right? Wow, it does what it says on the tin, right? And the first thing for that is the algorithm. So Jaro-Winkler and Levenshtein, and the names that was the strings we are comparing. So Stephen to the, this is our search screen, losing my ability to speak. The name we are searching for and the value in the table, right? So we can compare those. And we run that and we get the same values that we did with UTL match. Exactly the same. It's just it's a SQL operator rather than a PL SQL function. Okay. So one of the things you might notice is that this is giving us the 0 to 100 scores, so the percentage scores. So it does that by default. If you want the raw scores, so Levenshtein, the number of characters, and Jaro-Winkler is actually just kind of the percentage to 0 to 1, we can use the unscaled parameter to return those raw scores as well, if you want them for whatever reason. Okay, so at this point, it's like, okay, that's nice, but what else does it do? Well, fuzzy match has a bunch of other algorithms it supports. And you say there's like n-gram, so bigram and trigram. Essentially, bigram splits these up into all the 2-character things, so ST, TE, EV, VE, and EN, and trigram's just the 3-character splitting up of those, and it asks how many of those match in the string we are searching for compared to the name. So we look at bigram, Stephen and Stephen, unsurprisingly, 100% match. Stephen with a PH has a 50% match. Why 50%? Well, it matches ST, TE, and EN. And Stephen with a PH also has, it's actually got 6 of those. So it's a 50% match because we got the PH as well. Trigram, the only thing that matches here is the STE. They're the only 3 characters in a row that actually match and are the same. So with the unscaled, it's asking how many of these matches are there. With the scaled, which is the default thing, it gives us as a percentage of the number of them that there are in total. So we can use that to kind of count how many consecutive characters are the same, these n-gram matching, which again could be useful in some situations. Another thing we could do is look for the longest common substring. What's the total number of characters in common? So we search for Kris. Hopefully that will match Christopher. And indeed, the highest match is Christopher. So by default, we get a percentage of the number of characters in Christopher, or 5 characters total for our unscaled. So we can see there's other ways we can look for the closest match here. So again, this is useful for like abbreviations and stuff like that, where we know part of the string, maybe not the whole string. Okay. So far we've looked at matching just one name. What do we want to match on family name and given name at the same time? So we've got Kris Johnston here, okay? Let's look at matching those with the Jaro-Winkler and Levenshtein. So we do that and we'll pull back. We can see the top two matches are Charles Johnson and Christopher Olson. It's like, neither of those are Kris Johnston, but they both get quite a high match, right? Particularly on Jaro-Winkler. Jaro-Winkler considers those quite well matched here. And it's like, not quite sure that's right, is it? And, you know, Levenshtein on Charles Johnson thinks that they match very well as well. It's like, I don't know. Maybe we want to match the whole words. We want to consider these separately. So there's ways we can do. We could split the string up manually ourselves, or we've also got a whole word match algorithm, which basically asks, do the words in their entirety are they actually the same? So we run that with Kris Johnston, and we see by default, no matches whatsoever. None of these things match at all, okay? Which is then not giving us false positives. However, we might still want to take into account, you know, slight differences, maybe typos, misspellings, things like that. There is an edit tolerance, which is the percentage of different characters, essentially. So we can say, these match the words with some fudge factor in there? And again, we can see now Charles Johnston matches, you know, to Kris Johnston in that situation here. So by default, it is exact word matching, and it's asking how many of those words match in their entirety. If you want to have some wiggle room, you can specify this edit tolerance in there as well. So this question, can we match on club columns? I believe so. I'd have to check that. Let's keep that in mind. If we've got some time at the end, we'll check that. But I'll have to check on club columns. Okay. So at this point, we've got you know, 23 AI, we've got UCL match and fuzzy match. You're like, well, which should we use, right? Why should I use one or the other? They both give the same results. However, there are some considerations. One is that these algorithms are case sensitive. They are literally just matching character by character. So if one of the strings in uppercase and the other's in lowercase, it's going to say they're different. Okay. So we can see we get quite a low match here because they're only actually matching the S at the start. So if we wanted to kind of manage case insensitivity with UTL match, we can upper or lower or whichever way around we want to do it so that they are in the same case. And now we get the same matches here. But what if we wanted to use collations? Like I say, this is something added in 12.2, which allows us to compare things case insensitively. So binary CI equals binary case insensitive, okay? And it says, compare that case insensitively. Are these the same if we ignore uppercase versus lowercase? Check that out. And the answer is, well, yes, it is. Yes, they are, right? They are the same characters, just in different case. So we can use this collate clause with fuzzy match, but UTL match does not take it into account. So we've got Stephen here. We're saying use case insensitive rules for comparing it. When we look at the fuzzy match, we'll get close matches, whereas UTL match, we will not because it ignores this. So you can see Stephen, exact match for our SQL operators, but almost no match or very much lower matches for UTL match because it is not taking into account those collations, okay? You might go, well, you know, what's the big deal in this, right? We can just uppercase, lowercase things and do it that way. And it's like, well, that's true. Yes, you could. But there are some advantages to being able to use this collation. One of which is you can actually specify the collation at the column level as a default for the column level. So by doing this, we're now saying all comparisons for first name should use AI, accent, and case insensitive rules. So AI has nothing to do with AI, LLMs, artificial intelligence. This is accent and case insensitive comparisons. So we do that. And we compare. So look, we've got Stephen in uppercase, but I've added a whole bunch of diacritics in here. I've got N with the Enya, is it acute or grave? I can't remember, and the little hat over the E as well. The fuzzy match, because we've put that logic, that collation on the column, it doesn't care. It will compare these as if they were just the same character. UTL match will not do that. So there is this advantage to being able to use these collations. Yes, you can use upper or lower to force case in UTL match, but if you want more powerful things, or it's kind of happen kind of by default, by declaring it at the column level, to use collations, you will need to use fuzzy match there, right? UTL match will just ignore this. And so I see someone saying about the data quality operators, fuzzy match, phonic encode. Both, it can be any of the data types, char, varchar2, nchar, or nvarchar2, so not clob. Okay, so thanks for pulling that out. So sadly, not clob, at least not for now. Okay, yeah, well, we can think about that a bit later if we want to. Okay, yeah, so thanks for digging that out the docs. Okay, all right. So we can see with fuzzy match, we can use these collations, which can be very useful, particularly for accent insensitive collations. We want to ignore diacritics and things like that as well. Whereas UTL match, we can't. Right, so let's just, this using NLS comp just basically means use the settings. So we're back to case sensitive comparisons. So at this point, it's looking like kind of a slam dunk win for fuzzy match. It has a lot more options to it. We can use collations, more algorithms. There is one little thing to be aware of, and this will be a bit more significant in a minute. We'll come back to this. UTL match works in PL SQL. Unsurprisingly, it is a PL SQL package, whereas fuzzy match does not work in PL SQL, at least certainly not at the moment. Okay, you can only use fuzzy match in SQL statements. Okay, so if you've got some existing PL SQL code, your upgrades to 23 AI, that you got existing PL SQL code that uses UTL match, to use fuzzy match, you would have to turn that into an actual SQL select statement. So just something to be aware of there. All right, any questions or comments on that before we kind of recap on this? In 23 AI, we can hash the names using something like an AI-based RAG. Could that also give a result? We'll talk about that. Hold on to that thought. We'll kind of mention that a little bit briefly at the end. Okay, we'll come back to that kind of thing a little bit later. Any other questions or comments here? Okay. All right. So where exactly can we use it in real time? I'm not sure what you mean by use it in real time. You can use these in SQL statements. They process the data. What you have to, I don't know what real time means. Okay, it's as soon as the data is in the table, you can run it anywhere. You can run a select statement. I don't understand that. You know, you have to kind of be a bit more explicit about what real time means there. All right, so let's just kind of recap on that. So in 23 AI, we've got better options for encoding, the phonic encode, which is a significant improvement on SOUNDEX. It's got the double metaphone. We can specify the length, how many characters we actually match, and there's the alternate one as well to handle different dialects, different pronunciations of the same characters. We can, the fuzzy match operator, which has Levenshtein and Jaro-Winkler. It's also got a refinement to Levenshtein. It's like Damarau something. It's just a slight tweak to it, really. But it also includes some other options for actually doing these fuzzy matching, some other algorithms, which could be useful in some cases. And then if we want to look at handling mixed case, so the collate operator, again, collate's been around a long time. This isn't a 23 AI thing. But you cannot use it with UTL match. You can use that with fuzzy matching. Okay, so we've got our options there. And, you know, we're putting these things into production, kind of find people based on their name, do better matching. However, Bosscat's not happy, right? They want the queries to be faster, right? You're like, it's all taking too long, all this matching. What can we do to speed this up? So first question here is, we looked at fuzzy match and UTL match, different languages. Which of these is actually faster? Interesting question. it's not quite as straightforward as you might think it is, right? You know, if you want to vote, have a guess now, just put it in the chat and let me know. We'll see what people think. But it's not quite as straightforward which of these is the fastest, right? Second question is like, how do we speed things up generally? We create an index. Well, what indexes are we creating here? How do we index these things? How do we do that? So we'll look at that. Finally, and some of you may be aware of Oracle Text. Oracle Text has fuzzy matching operations in it as well. So for free text search. So you're not familiar, Oracle Text has lots of powerful options for kind of free text searching. It includes fuzzy matching options in there. So we can create it with this index type, which is always cryptic, and I always forget exactly what this CTX sys thing is I need to put in here. There is a refinement and a simplification of this syntax in 23AI. So these two things are the same, just different columns. So create search index is simplest syntax for Oracle Text. Can this help us? Can this help us use an index to find things there? Okay, so SQL versus PL SQL, which is faster? They say, any of you feeling brave, give us a vote before we actually do that. Indexes, how do we create them? What are they on? How do they use? And then Oracle Text, how do we fuzzy match? Okay, right. So at this point, we're going to jump into a demo and these, right. So no one's been brave. No one's going to vote. Oh, come on. Yeah, let me down, right? So when we look at SQL versus PL SQL performance, so we're just going to loop through the table, doing the fuzzy match, both Jaro-Winkler and Levenshtein using fuzzy match. And we're going to do the same with Jaro-Winkler. These are basically the same thing. I've just swapped out which thing we're actually using here. Yeah, someone's saying it depends on what you're doing. Oh, come on. Why does it depend, right? Anyway, so we'll run these and let's see what happens. So this is going to take a few seconds to actually process as it just kind of loops through these. So say it loops through the table many times, and we can see some things here. We can see now SQL about just over a second, PL SQL about 8 seconds. So SQL here in this example is clearly much faster, right? So SQL operators for the win, right? We should use these. We can just forget about UTL match. It's clearly so much slower. Row by row, slow. I mean, it depends what you're doing. You know, we're just looping through here, right? We're not actually doing any processing in the loop. We're just fetching the data essentially. So it's not really I'm not sure it's really row by row processing here. All the logic is in the SQL. However, so we'll do the same thing with our SQL, we'll run that. But with our PL SQL, let's first just bulk collect everything. Let's fetch all the data and then use PL SQL loop to actually do the UTL matching, right? So what's going to happen here? Let's have a look and see. And overall, hopefully this will be much faster. Yep, much faster. SQL, unsurprisingly, takes basically the same amount of time, just over a second. But notice the PL SQL is now actually faster, about half the runtime here. So it does depend on what you're doing here. Specifically, if you are already in PL SQL, UTL match is faster. You know, there is kind of thing to say if you can do it in SQL, SQL's faster, and generally that's true. But if you are in PL SQL, you've got all the data, and you're just crunching it in PL SQL, it is in fact much faster than invoking the SQL engine, right? So even bulk collecting all the data, and now this may not be an exactly fair test in terms of how loading it in, but it shows that it's not as clear cut, which is 100% faster. It depends on what you're doing, and you will need to test on your actual data and see what's going on here, because it probably depends a bit as well which algorithm you're using, the strings you've got, and things like that too. So it's a good idea to match whichever language you're using. If we're doing the processing in SQL, use the SQL operators. If we're doing the processing in PL SQL, use UTL match as much as possible. Right. What about indexing? Let's look at indexing function code. Well, let's create the index there. Created. Nice and easy. Does the job. Fantastic. Okay, we've indexed it. Notice we've done the 12-character encoding. So we can say Christopher and Chris, various spellings of Christopher compare. We look at plan, and indeed, the query does use the index, right? However, we need to know exactly what the terms we are searching for here. We need to know what length is. Are we double metaphone or double metaphone alt, right? If we change the characters, the number of characters we're matching here, we now no longer use the index, right? It's a function-based index, so we have to match exactly, right? There are some wiggle room with that, but if you take it as if there's any difference with the function you create and the function you use in the where clause, it probably won't get used. And we see indeed it doesn't. So you need to think carefully about how many characters you're encoding and what you are comparing on. Certainly, if you want to do lots of different comparisons and you want to take in double metaphone alt as well, and things like that. Okay, so things like that. So we can index phonic encode, but we need to be a little bit careful with our where clause. What about fuzzy matching, UTL match? Let's try and create it on the PL SQL package, and function is not deterministic. Now, I'm not entirely sure why function is not deterministic. As far as I know, these are deterministic algorithms, so maybe they've just not been decorated with a deterministic clause, but that's where we are today. It's considered not deterministic. We can't create that index. Okay. So, and it's the same for all the other UTL match functions, right? They all raise this error. What about when it comes to fuzzy match? Well, let's do that. Let's create the index. We can create the index. That's looking good. Let's use it in a SQL statement. So we're saying, greater than 80% fuzzy match, and does do the range scan. Looking pretty promising, right? Well, yeah. What have we created our index on? We're searching for the string Stephen, okay? What happens if we search for a different name? Well, that is not what is in the index. So we get a full table scan. The database can't use it because there is a mismatch between what's in the index and what's in our where clause. So technically, yes, you can index fuzzy match. However, for almost all practical use cases, I'm not sure this is actually going to be that useful. I mean, if you've got a data set where you're going to be comparing the same search string many times, maybe, but I think that's quite a niche example. So we can fuzzy match, create indexes on fuzzy match, but in practice, will we? Probably not, okay? So just bear that in mind. So what about Oracle text? Let's come back to that. So this will allow us to kind of index anything, right? So you say these two do the same things, just first name versus last name, and this is the 23 AI syntax for that. Okay, so first thing is, in order to use this, we've got to use the contains function, right? So we'll run this, contains Stephen. First thing to notice is it's automatically case insensitive, right? I removed the collation. I did remove the collation from this. So we don't need to do anything special to get case insensitive queries. So we can do an exact match there with contains, and we can see it does use that index. So you have to do this contains to use Oracle text indexes. If you look through the documentation, you'll quite quickly hopefully spot, just do a Control F, find, there's a little fuzzy operator. Oh, that sounds good, right? Let's check it out. Fuzzy Stephen, and indeed, we find everyone called Stephen that we would hope for, right? V and PH in there. So this is looking promising. Let's look at Kris. Well, okay, there was no Chris's, but there was a Christopher. They've not been fuzzy matched, right? Well, what can we do here? Well, there's a couple of optional parameters here. So they match the similarity score and the number of expansions, basically how many things it actually compares. So set this one, lower value, more results. Second one, higher value, more results. So one is the lowest, I believe 5,000 is the highest. And we can see now matches Christopher and pulls back Charles as well. So we get fuzzy matching there. So if you're going to use this, you probably want to look at tweaking what these values are here. However, what happens if we do Christopher with a K? No matches again, right? So fuzzy is an internal algorithm for Oracle text. So, it's an internal proprietary algorithm. So I'm not going to share the exact details, but one of the things we can see is, again, it's considering the first character for whether it's a match or not. So this first character is significant, which could be a bit of a problem here. So does this mean Oracle text is kind of useless here? Well, Their alternative. There is something else we can do. There's this in data. And what this allows is, again, this is an internal algorithm that combines fuzzy and kind of sounds like logic. I don't think it's actually a SOUNDEX. Again, it's an internal proprietary, but it combines these things. Now, this is actually, if you've got XML or JSON or something like that, the idea is you can pull out attributes within it, but we can also use this end data to create these named data stores and pull out bits with column values. So we need to set these preferences up first, and then we'll rebuild the index to use these things. So our named data store and our section group. So we need to create those first, then either rebuild the index or create it with these parameters and these settings. So we can use this end data, and we can do an end data with Stephen. You're like, well, okay, we've only pulled back Stephen with a V. That's not helped us, right? Well, again, there are some optional parameters. The one we're really interested in here is this fifth one. So we want to set that low. So by default, excuse me, this is like a minimum threshold. Anything below that, it'll just won't return. Set that as low as possible to 1, and see we can now get quite a few matches here. We're getting our Stevens, V and PH, and a few other matches as well. So this is looking much more promising. What happens if we do Kris? Well, we get Christopher, Charles, and Curtis, and we can see our scores there. And what about Christopher with a K? Well, again, Christopher with a CH is now our highest match. So I would say if you are looking at fuzzy matching with Oracle text, look at using this end data. It gives me much better results, right? I'm not an expert in Oracle text, but it's certainly seen, and this is what the director of Oracle text directed me to. She said, look at this, it will help. Just remember, you've got to create these things first. All right. Any other questions or comments on this before we move on? So a couple of things to see thing. So someone's saying, try again, SQL again with array size 100. Right, well, the SQL is in a PL SQL block, right? So it's a PL SQL Blue. It's already fetching in, PL SQL's already optimized to fetching batches of 100. This already is effectively set array size 100, okay? Because it's in PL SQL there. So it's because it's all in PL SQL block. So that should already be accounted for. Maybe we could create a deterministic function on top of it. That might work, I don't know. Maybe we've got some time later, we can check that out. Does Oracle text work in standard edition too? I'm not sure. For the SQL statement, not the PL SQL. I'm not sure what you're saying there. Like this is the SQL, right? This is the SQL statement I was comparing the performance of. And we're just fetching the data, but only doing it in a PL SQL block, right? You've lost me. You know, we're just looping through all that, okay? So let's just, that's a good question, actually. Is it on, so actually, if you've got these kind of licensing questions, a great place to check is the Oracle Database Features and Licensing app, right? So this is the Features and Licensing app, shows when things were added, shows about licensing as well, and we can see Standard Edition 2, see Oracle Text. Okay, so now one of the things is Oracle Text has been around a very long time, so these are kind of new things. So we can see SE2. Another thing you might want to check out is the licensing guide, and I'll update, make sure I'm on the latest release. The database licensing guide. Like I say, whenever you've got licensing questions, look at these. The licensing guide is the Bible. I would not say anything without looking at this right first, because we can find otherwise. Oracle text, it doesn't seem, okay, Oracle text isn't appearing as a separate thing here. If it's not listed, if something is not listed in the licensing guide, it's included, right, as part of the licensing. It's just part of the standard release. And I'm not seeing Oracle text listed here. So obviously, as always, double, triple check. Don't take my word from it, or some speak to your licensing guide and stuff. But as far as I can tell, that means Oracle text is available in all offerings. Okay, so check out the licensing, check this. If you can't find it in there, that means it's actually just available always, okay, as a rule. But as always, double check, right? In your things, okay. Yeah, no, I'm not running standalone SQL, right? It's SQL inside a PL SQL block, right? It's all inside a PL SQL block. It's all in a big in thing. It's all in just one big. Like I say, you can get the script. I'll share the links in a minute. You can get it. This timing package is just a thing I built to just capture the start and end times and calculate the differences. It's in the setup script as well. So we're literally just running that SQL statement however many times. If I run it once, it's all too fast to check. That's why I've got like 10,000 here. Any other questions or comments before we wrap up? All right, so see anything else? Okay. All right, so let's just recap on that quickly. So SQL versus PL SQL. I think the big takeaway there is match the target language you're in. If you're writing a SQL statement, use the fuzzy match operator. If you're in PL SQL and have got the data, just use UTL match. I mean, there will probably be exceptions, but generally match the language you're using. When it comes to indexing, you can't index UTL match. They say, could we create a deterministic map wrapper? Maybe we'll have time to check that in a second. You can index fuzzy match, but in almost all circumstances, I would say it's almost useless, right? Phonic encode, however, there is still some considerations, but matching phonic encode does work pretty well. Finally, Oracle text. Oracle text has contains query, as again we saw, it has its proprietary fuzzy matching, which kind of works, but a bit like SOUNDEX is a bit limited. Or there's NData, which combines fuzzy and sounds like and does a better job. And of course, this is then the contains query will use the index, right? Whatever you do. So isn't quite as fussy, shall we say, as some of these other approaches when it comes to counting as a match. So there's a couple of final things to think about. One is we've looked at things and we've found different matches, and it's like, well, what actually counts as a match here? These things are kind of gives us percentages and say, are these similar? We're going fuzzy match. We want to find some cutoff. Well, what's the value? When do we say these are the same? Right? I don't know. Right? This is the classic "it depends" thing, and it's like, well, what does it depend on? Well, I think the main thing to bear in mind, the lower you set this cutoff, the more false positives you're going to get. You're going to match things which are just different to what you're expecting. The higher you set it, the fewer false positives you're going to get. Fewer false negatives you're going to get, but you'll get fewer matches overall. Okay. So the lower it is, you'll get more matches. The higher it is, you get fewer matches. Which of these are you more? I think I messed my slides up here as I was looking at that. Oh dear. Oh well. Anyway, so this is my kind of opinion on this. Obviously, you got to think in your use case. I'd set this lower if it's a manual search, so someone's actually typing in something, because you want to pull back possible matches, and it's up for them to kind of filter that. Obviously, sort it by what the match percentage is. If you're doing automated matching, I would set this threshold quite high, because you don't want to accidentally match people that are in fact not the same, right? And you probably want to have other matching as well. I worked for the NHS, the health service here in the UK years ago, and in order to match people, they actually you had to match on something like 5 points of ID. I think it was first name, last name, date of birth, NHS number, and address. I think there was like 5 things. You had to match on 4 out of 5 to be considered a match, right? So if you've got automated matching, you probably want to set this as a higher threshold. Whereas if it's search, probably want to set it a bit lower and let people decide if it's the same. Found the blog by Sandra Suarez. It's a really good use case of actually building. They use fuzzy matching and the Jaro-Winkler. Basically, people were creating new customers, but creating lots of customers with the same name but different variations. Things like limited spelt out and LTD, because it was exact matching beforehand. So they use this quite successfully with Apex an Oracle ERP to kind of reduce these duplicate customers, which obviously creates all sorts of downstream problems. So I think that's a really good case study of how you can use these algorithms to understand what's going on. Just a kind of final recap on this, if you want to do fuzzy matching, 21C and earlier, you can use like. You've got to be pretty sure what you're searching for and know what the wildcards are. SOUNDEX, okay, you kind of squeak by, but it is quite limited. And UTL match for those things. And Oracle Text, again, Oracle Text has been around since 8 something, a long time. 23II, that's expanded with phonic encode, which is much better than SOUNDEX, and fuzzy match operator, which complements the functionality in UTL match and expands it further. When it comes to performance, look at which algorithm language you're using, look at the indexes, and see if you can use Oracle Text. Final thing, there's some questions some of you have been asking. AI vector search, similarity search, right? Now, this is something this is another way we could do it. Now, things to remember with vector search is, or AI vector search, it's doing similarity search, so it finds similar names that can include different spellings, but also names that are spelled completely differently, names that are conceptually the same. So it may not give you exactly what you're looking for. But that's kind of nice lead into next month. We will actually be looking at AI vector search. We've got a special guest. So we've got Ronald from JobRunner. So this is an open source system which is using AI vector search in Oracle database to optimize their processes. So next month they will be joining us to show how that works in actual practice and real world case study. Those of you who are regulars, notice different time. Normally we're every 3rd Tuesday of the month. It's the 2nd Tuesday of the month, so 10th of June. Normally we're at 2 p.m. UK time, or at 4 p.m. UK time. So we're kind of a week earlier and 2 hours later. So if you want to know about vector search and Oracle database, check that out. That's coming up next month. And with that, all that's left to say is I really hope you enjoyed this. More importantly, I hope you learned something and hope to see you next month. Goodbye.